Little boxes on the hillside, little boxes made of ticky-tack. Little boxes on the hillside, little boxes all the same. There's a green one and a pink one and a blue one and a yellow one. They're all made out of ticky-tacky. They all look just the same. And the people in the houses all went to the university, where they were put in boxes. They came out all the same. And there's doctors and there's lawyers and business executives, and they're all made out of ticky-tacky. They all look just the same. And they all play on the golf course and drink their martinis dry. They all have pretty children. The children go to school, and the children go to summer camp, and then to the university, where they are put in boxes. They come out all the same. And the boys go into business and marry and raise a family in boxes made of ticky-tacky. They all look just the same. There's a green one and a pink one and a blue one and a yellow one. They're all made out of ticky-tacky. They all look just the same.
All right, everybody. Stay outside that box. Welcome to the show. My name is, Zachary Zabala, or Good Times for All if you prefer. Hope everybody is having a beautiful day out there. Sorry it took a little longer than I expected. Karen was really ladling gravy and had some great callers. If you missed the show, go check it out. That's Karen B on YouTube channel, and Rockfin if you are a member over there. So today we are going to talk about gathering electricity from Earth's resonant frequency. Now, this is kind of like, to me, it's like gathering electricity just from the air, but it's not the same thing as like putting up something into the air and just gathering the electrostatic charge and converting that. This is a little bit more in depth. This took a lot more dedication to figure this kind of stuff out, and it's really old, actually. This isn't a new idea. This is something that's you'll see. It was actually thought of, they claim, by Nikola Tesla himself, that this would be possible. And then another gentleman came up and figured it out. But this is just MIT news on campus and around the world. Oh, sorry. I've been trying to drink some coffee. This is usually right around my nap time. You old folks like me know what I'm talking about. So, converting Wi-Fi signals to electricity with two new types of materials. So this is just showing that researchers from MIT and elsewhere have designed the first fully flexible battery-free rectenna. Now this word rectenna, this is something that I had never really heard of. You know, a rectenna, what is that? A device that converts energy from Wi-Fi signals, really radio frequencies, into electricity that could be used to power flexible and wearable electronics, medical devices, and sensors for the Internet of Things. That's kind of scary, but it talks about, I left all the links to these articles if you really want to go through them in depth. I read over most of it. It gets down here and talks about the different types of materials that they use and how they're able to convert more and more of this electricity that's out there into usable electricity. They're getting higher percentages. Like you put out so much, like this one got about 30%. And then the gallium arsenide achieve around 50 to 60%. Now I found other articles that said they're up to 85%. This is 2019. So this is over 3.5 years old now. This is just one that I found interesting. A lot of it has to do with the shapes and the turns and this and that. It's really neat, but it's not new. And let's see, team is planning to build more blah 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 blah. No. Okay, semiconductors. So this is doing it using semiconductors. Okay, and now what I'm gonna present here, the idea is not like this. It's more like a Tesla coil gathering energy. And this also works. But first we'll go into, let's see, here's Carnegie Mellon University. And this is the one envisioned by Nikola Tesla. Wireless energy transmission was made possible in the 1960s with the invention of the rectenna. So he didn't actually like create a rectenna, but it was something that he was working on. So it's just a blend of the word rectifying and antenna. Rectennas are receiving antennas that convert energy from electromagnetic waves into electricity. Passive RFID cards are one familiar example. Use energy from the radio waves emitted by the reader to transmit back their identifying data. So if you don't know what an RFID card is, I'm sure that they're in most licenses now. I know they're in pretty much every single type of credit card you can get or debit card. If you melt it down and get all that, not with fire, I mean, you probably still find it with fire, but if you use alcohol maybe, ether, some type of, there's a way to do it. You put it into this solution and all the plastic just kind of melts away and you're left with this little tiny chip. And then it has two pieces of wire that come out and do this weird thing. Well, that is a rectifier or what are they called now? Rectenna. Yeah, rectifying an antenna. Okay. Blah, 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 blah. It talks about the hertz and this and that. See, this is where I get lost. This is where I need people more like Bob and people who know about all of these kind of frequencies and how much, because there's a way to do it, but I don't know if you're going to get that much electricity from it. So this is just kind of showing that this is possible. This is well known. Even in the mainstream, they're actually starting to do this kind of stuff. There's going to be people selling it. Now, this is what got me thinking. If you've never heard of this young gentleman, his name is Parker Edmondson. He is he's got a really interesting personality. And he's done so many videos on, I'm going to start with this video just to show you. This is him at a young age. What our children should be learning and knowing at young and being taught at these young ages. And you'll see what I mean when we get into more of the stuff that he's already done.
The whole sidewalk with chalk. There's a lot of sidewalk. Sidewalk, right. Oh, it's a stick. Somebody must have dropped it. It's okay. I'll pick it up. Children, are you going to come down here and draw? I make a magnetic field. Actually, it's going to take you a What are you going to draw, Juliana?
Okay, today I'm going to show you the effect the magnifying transmitter has on a fluorescent light bulb. When
Sorry about that. I won't mute myself during the videos anymore. Thank you, Vegan Berserker, for letting me know. Vividness, Sue Finelli, hello. Effie Nation, what's up? Jeremy, I want to know more. Great channel. Lunderground, Aisling717, or Cammy Nodell if you prefer. Martin Haley, Flat Earth Ship Bear, Nemo, Big Skinny Matthew, what up, brother? Salted Cedar, Thunder Chicken, Spicy Sarah, Candace, Jennifer Kiesling, Boston Ray Mudflood Adventures, Jenny T.I. Murphy. Thank you all for coming and hanging out. Ex Globetard 2, love it. Called out the Nikola Tesla right from the beginning. And Lev Kung Fu Shaolin. How we doing? But yes, this young man is I want to show you some of the stuff that he's built, and just that it's not really that hard to comprehend this stuff. It's now it's amazing what he's done, but that he's showing that anybody can go do this with, Coke bottles and, you know, copper wire and just a few little things. It's really amazing the amount of knowledge this young man knows. I don't think he'd strike me or anything. If he does, it's no big deal. But for fair use, blah, 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 all that good stuff. This is Parker Edmondson. Please go check out his channel, folks. Now, he does a lot of videos from he loves the 1920s. He has a car from the 1920s. He has radios from the 1920s, sewing machines, like everything, furniture. He just loves that era. And it's almost like he's from there. It really is. He's just a very bright young man. And yeah, so this one's about 3 minutes long. It's not too long, but just check out this setup he's got going in his yard. This is his magnifying transmitter. So this is what Tesla was building up in the mountains to magnify electricity out to everybody. This is what Tesla was envisioning.
Okay, today I'm going to be running the magnifying transmitter that I built and tuned to transmit at a frequency of 168 kilohertz, or 168,000 hertz. So I noticed in my previous videos about the magnifying transmitter, in the comments, that people think that one receiving coil built to receive the power from this magnifying transmitter will only power one LED light bulb. This is not the case. It can power many LED light bulbs on one receiving coil. I also noticed in the comments that people want to know how many LEDs I could run off of this thing. Well, considering I'm feeding the tank circuit with 50,000 watts from this transformer, I could at least run 50,000 watts. But I know I can run a little bit more than that, because this whole thing is a transformer as well. And this transformer is far bigger than this one. One thing that's special about this transformer, the magnifying transmitter, is that it can tune to certain frequencies. I also see in the
Which is so important, folks, the tuning to certain frequencies. Now, everything has a frequency. Thank you, Cami. She just dropped Parker's channel there in chat. Thank you so much. Now, everything has a frequency. Humans is around 5 hertz. The Earth actually has multiple resonant frequencies in the low band. And I'll show you what I'm talking about here near the end when you start looking into the Schumann resonance. And now the Schumann resonance is the strongest one that's happening, the frequency. It's right around 7.83 hertz. But there's actually one at 4, at 7, at 14, 20, 21, around there, 27. And all within, it was around 50 hertz, but actually the Schumann resonance has been rising, which so many, I've been seeing a lot of, the new age group using this as saying that this is a time of enlightenment, that the magnetic field changing the way it is, resonating at a higher frequency throughout the day, is actually, helping people wake up to things. Now, there would need to be some real extensive research done, and it may be being done, who knows, but I'm not going to make that claim. So here we go. I just wanted to mention that part about frequencies and how important frequencies are, and that they are in everything.
The comments that people want to know how this is wireless. Well, this is like a radio transmitter, and the receiving coil is like a radio. The only difference being this electricity is sent into the ground or the earth, and the earth behaves as the wire. So instead of stringing up telephone poles, you have the whole planet Earth, or the whole sphere of Earth is the wire.
So when he says it's the wire, it's the capacitor. It's that he turns the earth into a capacitor plate. The top of his machine will create a field going out like a pulse. It's amazing how far it'll go if you tune into that frequency. And then it turns the earth into, the other part of the device. You're not using a wire that runs all the way there. You're using the earth. And it's how things should be done, in my opinion. So let's go.
First, I will throw the switch for the rotary spark gap. The rotary spark gap acts as a switch which opens and closes at a certain frequency to control the charging of the capacitors in the tank circuit, which includes the primary of the magnifying transmitter, which is an inductor, and the capacitors. That primary of the magnifying transmitter is also the primary of the transformer, because the magnifying transmitter is a transformer. So this 400 amp knife switch right here goes to the transformer, which feeds the tank circuit.
I'm just saying, I want to flip a switch like that one day. That looks like something out of some Frankenstein lab, something or other. I want to throw a switch like that before I die. That's one of my bucket lists. I have a weird bucket list. I want to flip a switch like that. Just saying.
Circuit, so that 50,000 watt transformer. This meter right here shows how many amps the magnifying transmitter is pulling. And this thing right here is a welder that I'm using to ballast the transformer. Because if I didn't do that, it would take in more and more current until it caused a brownout. Okay, here we go. Now I will light this fluorescent tube wirelessly.
Did you see how bright that LED got? Oh my goodness. Now this is wirelessly. It's not hooked up to a receiving coil, which would gather that certain frequency. This is just in the air, the electrostatic near that generator that he built. And this is the electrostatics being put off into the atmosphere around him. This is wild. Now to get it to light up this far away is, man, that's a lot of power.
Okay, today I'm going to show you how to make a...
That's just wild. Sorry if that was so loud, too loud. But yeah, so that's his coil, let's back up.
Okay,
his magnifying transmitter. So he's transmitting electricity. Now remember, he said it, I think it was 166,000 hertz. So now we're going to look at how he teaches you how to build a receiver coil to pick up his electricity. When he flips those switches on, you yourself, can pick up that electricity. And we're going to show you how far away, they claim to have done it. Again, I've never tried any of this stuff. It makes sense to me in my head that this is possible. And, I haven't built a receiver coil, but I'm not sure, Brian. Where's the current? It's not like he's gathering it from the air. It's probably just from his house. And then he steps it up so many times with those transformers that it gets that strong. Bob could probably explain it a lot better. But yeah, this one, he explains a lot more about the length of the wire used and this and that. And that has a lot to do with collecting this energy. You have to have your antenna or your wire collecting it the right length in order to gather that frequency. It's really, really neat. So here we go.
Okay, today I'm going to show you how to build a receiver coil from start to finish, all in one video. So here are the materials you will need. You will need at least 1,464.2857 feet of wire. I recommend buying 6,290 feet of 26 gauge magnet wire on eBay because it is $58. That's the best deal. You will also need at least 395 feet of 14 AWG magnet wire. You will also need a coil form. I use a quick tube from the Home Depot, and the circumference of it is 25 inches. So the diameter is 8 inches. You will also need at least one 3-volt 20 milliamp LED. I recommend getting a different color besides white because you can see different colors better. You will also need two 1N4007 diodes. And you will need sandpaper. The total cost of all the materials should not exceed $140 if you build a coil exactly like mine.
Now, that was 2021. So may have gone up a little bit. We'll see.
The wire is the most expensive part. So before you wind your primary coil, you should know that I'm transmitting the electricity at 168 kilohertz or 168,000 hertz.
So what do you mean? 168,000 cycles per second. That's a hertz. Rectifier diodes. So that's his wow, okay. Yeah, I'm still not sure. See, Bob knows a lot more about all the little pieces and what they do. Different types of capacitors and diodes and resistors and transistors and all that good stuff. Yeah, I was thinking about it, how to try to explain this to people the other day. Like, okay, learning about electricity is like standing in front of the world's biggest ocean, right? Whichever one it is. Now, after I've learned all I have spending these last few years studying electricity so much, now it's like I step up to, the shore, and now it's the second world's biggest ocean. It hasn't really gotten that much smaller. There's still so much to learn. And it's it's going to take me some time to get a lot of this next stuff down. Just the lingo. That's what it is. It's like learning another language. But yeah, that was my comparison. Like, how do I explain to people, because they think I know all this stuff about electricity, and it's like, no, I don't. There is so much to learn that it's really, I've scratched the surface of electricity. And it's more like the nature of electricity that I comprehend. Once you start forcing it into wires at different amounts, that's where you lose me right now. But that's something that I will remedy for sure. That's on my bucket list. So here we go. Sorry.
That means
rambling.
that the receiver coil primary needs to be wound at a fourth of a wavelength of 168 kilohertz. This is 1,464.2857 feet. So since we want the quarter wavelength of 168 kilohertz in inches, we will take the quarter wavelength in feet and multiply it by 12 to get it in inches. Now you will want to measure the circumference of your coil form. This coil form has a circumference of 25 inches exactly. Once you have measured your circumference of your coil form in inches, divide this number by your circumference to get the amount of turns you will need of number 26 wire for the primary.
So you hear that? You need to know exactly how many more turns you need for, it's like a different part of the coil. This is your main coil here. But when you come back and look here, you'll notice, where's it at? Come on. Okay. Oh, right here. What the heck?
Get it in inches. Has a circumference.
See this wire? This is different. This is his smaller wire. This is his main coil. That is the 1600 feet. And this is the smaller one down here. Like I'll show you on my Tesla coil, I have this one. Where are we at here? Right here. So this is my main coil right here. But down here at the bottom, if you can see it, it's got a few different, I think four winds of this certain. So this thing really isn't designed to gather any certain type of frequency. It's not tuned. You have to have it tuned like this. The wires have to be all the right perfect length and this and that, kind of just like an antenna. To catch the bigger, waves, you need a bigger antenna. Well, here we go now.
Of 25 inches exactly. Once you have measured your circumference of your coil form in inches, divide this number by your circumference to get the amount of turns you will need of number 26 wire for the primary. Once you have wound your primary to a quarter of the wavelength of 168 kilohertz, you will want to tune your primary to resonate at 168 kilohertz. So to tune your primary to resonate at 168 kilohertz, you will need an oscilloscope. You will also need some sort of a metal object. I recommend using an empty soda can if you don't have a toroid like this. And then you'll want to connect the ground on your oscilloscope lead to one side of a 4 kilo ohm resistor. And you will want to connect a 1N34A diode with the line on the diode facing the metal can or a toroid, whatever you use. And then you'll want to set your oscilloscope probe to 1X. Also, on the ground lead of the oscilloscope probe, you'll want to ground this to an earth ground. You will also need a signal generator capable of generating up to 20 volts, and you will need it to be able to generate a sine wave. And it must be able to go up to 168 kilohertz. So to tune your primary coil, you will want to keep it clear of all objects and people for at least 4 feet. You will also need to raise your primary coil off the ground at least 2 feet on a non-conducting surface. Now to the bottom of your primary coil, take the wire coming off the bottom, sand it really well so that all the insulation is gone off the end of the wire, and then connect it to the negative of the signal generator. The positive lead of the signal generator should go to an earth ground. So you have grounded your oscilloscope probe to an earth ground, and you have grounded your signal generator to an earth ground on the positive lead. So here's a schematic explaining all the connections. Maybe this will explain it better. Here's the oscilloscope.
See, this is where they really lose me. Even what he was talking about before, it's a different language. It really is. But the concept, once you get all the wire, the electricity through the wires and it does what it does, then I'm starting to grasp that concept. But all the stuff in the wires, not so much. Yes, I know, Cammy. I wish I could download this info like in the Matrix. Wow. Yes, and he is writing in cursive, Nathan. For someone his age, that's not very common.
Oscilloscope. Here's the 4 kilo ohm resistor, and here's the 1N34A diode. And there's the empty metal soda can, or toroid. So the sensitive part of the oscilloscope probe, which is the hook part at the end, connects right there, and the ground of the oscilloscope probe connects right there and goes to an actual earth ground. And here's the receiving coil primary, and the bottom of the primary connects to the negative of the signal generator, and the positive of the signal generator.
Okay. See, he's talking Greek to me again. So I'm going to fast forward to the cool part, but the link is in the description. Please go over to Mr. Edmondson's channel and at least check it out. I'm not telling you to subscribe or say I sent you or any of that stuff. Just go check out his channel. He's a very interesting young man who obviously doesn't spend a whole lot of time watching television. I'll just say it like that. But we are going to fast forward to him. I mean, look, he's sitting there playing with the oscilloscope. He shows you how to do all of it. But then I'm pretty sure at the end, is this the one? No, that's not the one.
Okay.
Okay. But we will go to... So this is a friend of his that, we were already done with that part, who built his receiving transmitter that he just taught us how to do on this one. This is improvements to the receiving coil, but this one right here, no, it was this one and back one. I want to make sure I get it right. How to build a receiver coil to receive, now that, like he says, it's his wireless electricity. It's the stuff that he's putting out from his backyard there where he built that big thing, putting out all that charge. So a gentleman took up his offer 918 miles away in Wisconsin. Now he's in Louisiana. So we're going to check out the rest of this. It's only a couple minutes, but really interesting stuff. I would love to try this, to build my own receiving coil and, ask him to turn it on. He actually just moved, so I don't even know if he has access to that, his coil, that big giant coil he built. I don't know. But check this out. This is really neat.
When held up in the air near it. I will also be showing you the receiving coil lighting the neon light bulb orange in the nighttime, in the darkness. Okay, here we go. That is completely wireless. Now I will show you where the receiving coil grounds connect. The bottom of the receiving coil goes through this wire into the earth right over here. And the top is grounded by that bird bath.
Oh, Chicago to Texas.
Real quick, just to let you guys know what's going on. Every time you see my LED flash, that is not my electricity. That is Parker's electricity. That is his transmission from Texas. I'm in Illinois. We're about 2,000 miles away. I'm not connected to anything.
Not 2,000 miles, folks. Maybe 2,000 miles avoiding highways and stuff like that, but 918. Still a long distance, Texas to Chicago. So I was way off. I thought it was Wisconsin, and he was in Louisiana. Okay, here we go.
The only thing I'm connected to is the earth ground. Yep, there's the flicker. See that flicker? Yep, there he goes. See it? I'm not doing anything. That's Parker's transmission. Hell yeah. 2,000 miles away. Wireless electricity. Oh my god. Holy shit. Yep, there it goes.
That would be really cool to
What's
see
a
it.
wire,
No, I know
bro?
I like this already. What's a wire, bro?
Okay, today.
Very cool. Yeah, look at this is his 1928 Durant. If you just want to check out this guy's what he does, look at this. It's like he is from this time zone, time era or something. Just a really interesting character. Please go just check out his stuff. I haven't found anything that wasn't interesting, at least. Okay. So then I started looking into the. Now here's my idea. Okay. He was talking there about hertz. And if you were here earlier, we were talking about, rectennas and converting radio waves into electricity. This is actually taking radio waves and turning it into a DC. Now, this was first done in 1969, I believe. I should give that gentleman credit. They say it was envisioned by Nikola Tesla here, but there was actually a different gentleman who was the first to do it back in 1969. Did they mention it in this one? Ba-ba-da-ba-ba-da-ba. I'm not seeing 1969 anywhere. Let's. Well, if you look. Okay. Rectenna inventor. Now they have an optical rectenna with light. No. Okay. Was the inventor. See, this says Nikola Tesla was the inventor of the rectenna, but I couldn't find anything where he actually built one. William C. Okay, here we go. I know it's Cosmos magazine, but because they say this is how they do a lot of stuff with space and sending stuff to satellites and this and that. Nikola Tesla power. So introduce, and he actually demonstrated it. Okay, so according to this, so Cosmos, the science of everything. Because I mean, it's so hard nowadays. What you can believe. Where did they get their stuff from? So they say he demonstrated the concept of wireless power. William C. Brown. Now, okay, I've heard of this too. This is like him having the boat it was a remote control boat Tesla built supposedly. So I have heard of him demonstrating it, but it wasn't like sending large amounts of electricity that way. And I don't know. But yeah, that's the guy if you want to go check him out. William C. Brown, something to do with helicopters, high altitude helicopters, and sending energy. Yeah. Okay. Well, you can check it out if you want to. But this is what I don't want to say it's my idea, but now if Parker's putting off a certain frequency and you can build a certain coil to collect that, is there a coil we can build to collect the Earth's frequency? You know, they're doing it with microwaves now. They're doing it in all these different ranges. Can we collect the what they call the Schumann resonance? Now, I actually got a hold of Parker on one of his videos where he was explaining the distances because of the frequency, the length of the cord. And I asked him, how long would you, of a, wire would you need to tune it? And I was thinking backwards. It's kind of like gauging. The higher the frequency, the smaller the wire. So super low frequencies require a much longer wire. Now, 7.83 hertz isn't even audible. You know, you don't even, human beings can't hear that at all. I'm sorry, I'm just looking at chat. Alrighty, all right, sorry, here we go. And I went where, this is Lincoln Laboratory Publications. So, space systems analysis and test, electrical engineering, air traffic control. This is just a short one, but I wanted you to see that they've actually done this. 2 stations at a distance comparable with the wavelengths in the Schumann resonance frequency range, one in Europe and one in North America, have simultaneously monitored the natural vertical electric and horizontal magnetic components in the frequency range of 303 to 25 hertz. So that's what they say the range is. Like, but it's weird because I don't know. I got a lot more to learn about this. Schumann resonance stations are scarce, and even fewer stations have records with 5 to 6 year durations. The main purpose of this paper is to make comparisons at 2 field sites. Oh, so they didn't on the seasonal and interannual timescales. So they just took the Schumann resonance at 2 different places. And why do you think this is that there are that the Schumann resonance stations are scarce? Why would that be? This is the Earth we're talking about. We're spending how many billions of dollars a year to talk about, let's go guess on what that star is up there and what it's doing and what it's made of. But here on Earth, we can't have more stations gathering information about the resonance of our Earth here and what it's doing. And what's up with them not keeping records? I mean, seriously, what are our tax dollars going for? So this, they didn't even do it. Okay, this, I thought, but the 2 stations at a distance comparable with the wavelength in the Schumann resonance. So the distance between these 2 stations is the length of the wire you would need to get it tuned in with the Schumann resonance of Earth. So we're talking about Nagasaki, Hungary to West Greenwich, Rhode Island. Let's see. I don't even, you don't have to download anything on Google Earth, do you? I don't, this might be the first time I've ever tried it. No, not working for me. Oh well. I just want to see the distance between, you know what, I can look it up right here. Do it on Google Maps. So we're gonna start from, wait. Not from where I am. Okay. Nage Sink, Hungary. And we'll make a stop in Rhode Island, I guess. How do I do that? Good Lord. Do I have to hit directions, maybe? Oh, choose a start location. Okay, here we go. West Greenwich, Rhode Island. All right, come on. It won't give it to me. I don't know why. I want it as crows fly. Can't find a way there. What? You can't see that. Let's see. Can't find a way there. Are you serious? That's kind of weird. Gerard Morins. Electric resonance work. No, Scott, but I will. Thank you, man. So what I'm thinking is, it came out to, I asked Parker, how many feet of, the coil would I need to collect 7.83 hertz? And that's just one of the resonances that really sticks out. Like I said, there's multiple ones in that low range that resonate throughout the day, but the 7.83 is like the strong one, the one that's usually the strongest, I should say. So it came out to 31.4 million feet of wire, which is like, I think it was 6,000 miles of wire, which, is comparable with the wavelength and the Schumann resonance right there. So if they would have told us how far Greenwich, Rhode Island was from Nagasink, Hungary, I still don't understand. 4,250 miles. Thank you, Rethink. So you need 4,250 miles of copper coil. That's just crazy. And then it would have to be wound at a certain, you'd have to have all the stuff right, and then all the stuff on the bottom just right. And then we should be able to tap into Earth's energy. We should just get energy from that wire being that long and tuned in. Remember, you have to tune it. But once you tune it like it's a, like a radio, you get it locked in, that signal gets strong. I really wonder how much energy you could grab from that. Now, in theory, it should work. People are grabbing all kinds of stuff. They're able to grab microwaves now, and they can use really small little antennas because the waves are real small, and they can grab them with that. Now, to grab the wave of, the Schumann resonance, which is not a microwave at all. It's a huge wave, the distance comparable with the wavelength is from Greenwich, Rhode Island to Nagasink, Hungary. That's the distance you would have to be, apart or the length of your antenna to gather that. But we can coil it up and then gather and now if you gather a small amount at the top, and because you have so many winds and much of that coil, is it by the time it gets down to the bottom to you to where you're gathering electricity, has it amplified it that much? I would almost be scared to be around it when you were building this thing. But yeah, there's so much, and this is all based on stuff that I've read. I've never measured the Schumann resonance. That's one thing I would definitely like to look into to try to do myself. I want to measure the resonance of everything, of myself, of different types of plants, different types of materials. They say they all have their own frequencies. And I think that's something that, I want to start comprehending and not looking at it so much as in the wires, but naturally how all this stuff works and happens. But so that's my idea. Can we just build an antenna big enough to gather the resonant frequency of Earth? If you had, now they lay cables across the seafloors, right? Thousands of miles long. So, I mean, there's definitely enough copper out there. Look at all the copper in the telephone lines all around and all this kind of stuff. So there's definitely the copper's out there. Now, to have a wire that long, at the smallest gauge possible, it's like 940,000 pounds of copper right there. Just to give you an idea of the structure you would need to build something that big. The foundation of that structure would be big, I would think. Like really, like maybe the size of the pyramids, big. It's really weird how the bases of the pyramids are all kind of like really close to the same size. Just makes you think, you know, like what were they doing with these? Could it possibly be just the foundation that's left over? The structure itself is down, it's gone. Could that just be the foundation that held up these big giant energy collectors? I don't know. It's just an idea, but I think in theory, as far as what I'm seeing and what can be done right now, this should be able to be done. And this would be free energy. This isn't a human being creating electricity and sending it out somewhere. This is the earth sending out that electricity. If we can tap into that frequency and get it in tune, I'm really interested to see what kind of power we can get from that. Yeah. To explode. Yeah, the resonant. Yeah, that's one thing you got to be careful with is, you know, I mean, Tesla was shaking buildings by finding the resonant frequencies with a 10-pound weight supposedly inside of a box. And that weight, you know, hitting its cycle at that certain frequency, once he tuned it in with that building, they say the people inside the building thought it was an earthquake because the whole building just started shaking. Um, on bridges, you've seen, things happen where I think I forget what it was, one of those bridges, but something hit its resonant frequency and the whole thing just starts. And I've also heard that when soldiers march across bridges and things like that, that they don't march in time. They've been trained that once you're crossing a bridge, you no longer, left, 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 right. You don't do that anymore. Because if you start matching that bridge's resonant frequency, you can, bring it down. And it's neat. So this stuff is known about, but still, um, hidden at the same time. So, yeah, I don't know. How long have I been going? What time is it? 40, yeah, almost an hour. Okay. Yeah, so I guess I'm going to call it there, folks. So that was my idea of, I got it from watching this young man's videos and how he, set up his magnifying transmitter to go out at a certain frequency. And then when you build your receiver coil here, it has to be built a certain way, certain length, this and that, and then you tune it in to that, and it's like a radio. You can turn your radio on and you don't pick up all the stations at once. You have to, well, you do, but not until you tune it into that certain frequency does that one come through and really burr. For us older folk, we remember radios in cars that had to be tuned like that. You had a little knob, and they had little things. I don't remember the ones without, but there were places where you could tune it and then like set it to always stop right there if you hit a certain button. But I remember having to go through and just fine tuning it and getting it just right so that radio station comes in. And then when you're driving further and further away from, the radio tower, you're trying to fine tune it in just a little bit more, because when you go on those long trips to grandma's house, you get out of radio range and then you don't know what the channels are anymore. And I just remember stuff like that from when I was young. And yeah, this stuff it's real. You're tuning into certain magnetic waves. That's what they are. Magnetic waves at different distances. And once you line up your antenna to receive a certain distance of a wave, you will pick up that resonant frequency. And it goes from like almost nothing to like, yeah, I'm not getting anything. And then once you hit that tune, it's just like, bah, it's like breaking a glass with your voice. Once you hit that right resonant frequency of that glass, boom, it explodes. So yeah, just think about this stuff a little, guys. You know, we all know that, we've been lied to about so many things. And I think the best way to escape from, this thumb that they have us all under is getting our own way to create electricity. Not by having to burn some kind of material that you would have to buy, or, put forth all this effort and energy to where it's almost impossible to do nowadays on your own, to go and, mine enough copper and this and that. I mean, people do it. People cut down wood and and that's hard, grueling work. Wouldn't it be nice to be able to just flip a switch on your big giant Tesla thing and then everybody around for miles gets power? I mean, that would be pretty cool to me. No more, we have to charge you this, charge you that. Nobody's burning anything. Nobody's doing anything to create this energy. It's just coming from the earth. So that's where I think we should be heading. Ideas like that. And yeah, let's make this place a little bit brighter for the people that are going to be here after us. Yeah, it, you can do it one way or the other, or three ways. You can make it better, you can make it worse, or you can make no difference at all. It's up to you. And I'd like to try to make it a little bit better. And I think people like Parker, this young gentleman right here, the future looks bright. That there's still people out here like this, not just theorizing, but going out there and building the stuff and doing it. So cool. Um, oh, I'm not signed in. Okay. So that's it. I'm going to get out of here. Thank you all so much for joining. That was fun. I hope you learned something. Or if not, just found a cool new channel to check out if you're into electricity and stuff like that. But yeah, I think it's possible to just grab electricity. We don't need, you know, to create it somewhere else and then grab it. I think we can just grab it, you know, and we'll see. Maybe 31 million feet that's a long ways. But again, there's different frequencies. So if you go up to one that's like around 50, I think there's one that's 50 every single day. That wire just gets shorter and shorter. So we'll see. Yeah. So yeah, this is good times for all here signing out. As always, thanks for watching.